Hello everyone, in this presentation we are talking about heat switches and phase change materials. So phase change materials are another sort of thermal control solutions. So this is the reading sources and references for this part. So the reference for this part is mainly from the reference 1, book 1 of this list. As a refresher, basically we do have multiple ways of passive or active thermal control solutions. As you see in this list, in the passive systems, so let me activate my pen here. So in this list, you see the phase change materials that we have not covered in the course yet. But now that we are getting close to the end of the course, so I'd like to cover phase change materials as well. So heat switches sort of very similar to phase change materials, or phase change materials may be used in heat switches. So but I'd like to talk about heat switches as well, combined with these phase change materials. So a heat switch benefits the spacecraft because it reduces the heater power required to maintain the spacecraft temperature within allowable range. So let's see what is a heat switch. So basically a heat, or sometimes it's called a thermal switch, it's a switch between good thermal conductors and good thermal insulators as needed. So basically it switches the heat transfer on and off. Heat switch. It does not switch electricity on and off, so it is different from a thermostat. So here on the top, you do see a thermostat. So heat switches are different from thermostat. So the ladder controls heaters by opening, closing electric circuits at a given temperature. So a thermostat controls or opens and closes the electric circuit. However, a heat switch controls the heat transfer or heat conduction paths. So two different things. So if you look at the thermostat on the top here, it uses two different metal straps, this black and this red and blue metals attached side by side, and when they are exposed to a temperature difference, so initially they are like straight, and then when it's heated, let's say it goes above a set point, then one of the metals, the red one, will bend higher than the other one, and as a result the circuit will break and the switch will turn off. So that's a thermostat which works based on the temperature difference, of course, but it actually switches on and off an electric circuit. In contrast, a heat switch that you see here, when it's open, basically there is no, or there is little heat transfer between components A and B, or block A and B. So let's say A is the high temperature block and B is the low temperature block. When there is a gap between these two blocks, heat transfer is only by radiation. So heat transfer is not strong. So now if for whatever reasons that we will talk about, if somehow these blocks A and B come in contact, or if the gap decreases, then A and B will be connected and heat transfer will be augmented or enhanced, because conduction now is in place as well. So this is the concept of a heat switch. So basically a heat switch can increase or decrease the rate of heat transfer. A thermostat can actually switch on or switch off the electricity, the current of electricity. So two different concepts. So most heat switches that operate in normal spacecraft temperature ranges are passive devices, most of them, not all of them, so that automatically self-regulate their conductance rather than react to signal received from a controller. Some of them are active as well, so we will talk about. So heat switch is usually more than an on-off device. It is a variable conductance device. So in other words, in the case of a thermostat, it's either on, you do have electricity passing through the circuit, or it's off. But in the case of a heat switch, even if it's off, still there might be some heat transfer, but at the lower rate. Or some heat switches can actually have variable conductance depending on the temperature, set temperature and temperature of the cold and hot blocks. So here are some heat switch applications. So first, for thermal control of individual components. So a heat switch is mounted between an electronic box and a cold sink or a radiator. So as you see here, if this is the spacecraft structure that can be used as a radiator, and if this is the electronic box that generates heat, then in between a heat switch can be mounted, so individually for each component, so where the flow of heat from the electronics to the radiator is controlled. So when the temperature of the box rises above the switch set point, its conductance increases. So then heat can transfer to the radiator and then to the deep space. So a heat switch can thus maintain the temperature of electronics or instrumentation within a comfortable, allowable range. It can be used in the system level as well. So heat switches could serve as the basis for an entire spacecraft thermal control system, but they are not yet common. So they may be used for individual components or for most of the components or for the entire spacecraft. So this slide is related to the previous one. So we do have, so here we are going to talk about heat switch integration. Case 1, heat switch is mounted between a structure and radiator. So let's say this is the spacecraft structure and then the radiator on the right. So the switch maintains the entire structure of the spacecraft near the desired temperature. So this is, for instance, the system level thermal control using a heat switch. So on the left side, the spacecraft structure, multiple electronic boxes will be mounted. And then there is a switch between the structure and the radiator. It will turn on, it will switch on only if the temperature goes above a limit. It will switch off when there is not enough heat to dissipate. So this way, we can eliminate the need for additional heaters if the temperature of the electronics go below the allowable limit. So in another arrangement, this one number 2, heat switches mounted between components and structures. So each component in this case will be attached to the structure using its own heat switch. So this approach is more flexible compared to approach 1 because it provides more flexibility as it allows maintenance of different components at different temperatures by the selections of switches with different set points. So each switch can have a different set point because the electronics may not have the same allowable temperature range. So the second option is for component level thermal control, and it gives the flexibility of using different set points. So there are several types of heat switches in terms of the mechanism and in terms of the how they work. So we will talk about some of them here only. And when we talk about the mechanism of the heat switch, it means that how actually the process and switching on and switching off in the heat switch occurs. So the obvious or the most trivial one is by mechanical actuation. So in this case, heat conduction is assured by the physical or mechanical contact between the two cold and hot plates. So now how to make that contact possible? One type of mechanical heat switches is paraffin actuated. So the paraffin actuated heat switches have been used on multiple missions such as Spirit and Opportunity 2 Mars exploration rovers, MER or MER1 Spirit and MER2 Opportunity. They use this kind of heat switches, paraffin actuated. Another way of actuation is using shape memory materials such as shape memory alloys. So they change shape when exposed to different temperatures. And the third type of mechanical actuation is using materials with different coefficient of thermal expansion, such as the one which is used in a thermostat. Another way of actuation in heat switches is using a gas cap. In a gas cap heat switch is used to reject heat from the components this is for when it was used for a special mission on the Planck observation satellite. A gas cap thermal switch has been used that we will talk about this structure. And there are other types of heat switches as well, which are either under research and development or are less common. So we are not going to focus on those other types. All right, so here let's see the structure and configuration of a paraffin actuated heat switch. So the actuation by a mechanical means. So here we see A is when the heat switch is off. So we do see the radiator plate at the bottom, and we have the hot plate on the top for both cases. And when the heater is off, there is a gap between this contact plate and the radiator. So obviously heat can be transferred only by radiation between these two plates, not by conduction. So this area, this flexible tube is filled with paraffin. So paraffin is like it's a wax. It responds to temperature change and it can melt. So as a result, when the temperature of the hot plate increases, so that's the hot plate. So when the temperature of the hot plate increases, the paraffin will melt and expand, and then the connection between this contact plate and the radiator will be made. So as a result, conduction will assist radiation, and the heat switch is in the on mode in this condition. So, and thermal expansion of paraffin will result in actually expansion of this flexible tube, and then the connection will be made. And this is the reference paper for this kind of paraffin actuated heat switch. Shape memory heat switches use shape memory material such as shape memory alloy. So what is a shape memory material? So the materials which are at different lattice phases when they are at different temperatures are called shape memory materials. So examples of different possible phases, for instance, a hypothetical phase alpha and gamma. So phases of iron, alpha iron and gamma iron, temperature can affect the phase and therefore the volume of the structure. The way that the atoms in the structure are placed or are sorted out will change with a change in the temperature in some materials, not in all. And in some materials, the change is so significant and substantial that this change will cause a huge change in the volume and therefore a mechanical actuation. So the Naval Research Lab has proposed development of a shape memory actuated heat switch for a small satellite thermal control. A shape memory alloy is an alloy such as copper, aluminum, nickel is a shape memory alloy, and nickel titanium that can be deformed when cold but returns to the pre-deformed shape, remembered shape, when heated. So creating actuation. And this actuation is actually repeatable and it is reversible. So this can occur, many times because it's a linear process. So shape memory alloys undergo a lattice structure phase change at the prescribed temperature. Therefore, when let's say if it's using a heat switch, when the temperature of the electronics go above a limit, then the shape memory material will be actuated, for instance, will expand and make the connection, and then when it goes below a limit, it will transform to another phase and then will contract and break the contact. So that's basically how it works. This is another type of proposed heat switch based on using differential thermal expansion. So that's the reference and this is the schematic. So let's say at the bottom we do have the electronic box, hot plate for both cases. And then it's made of a cylinder with the core part. So the core part is a flexible rod like another metal, and then the cylinder is a different metal. So the thermal expansion coefficient of these two metals are different. As a result, at normal temperature, at the off position, when it's switched off, there is a gap. So heat is transferred between this red hot plate and that disk, and then the radiator only through this central flexible rod. So this rod does have a flexible joint as well, which is connected to a disk, and disk radiates to the radiator. So it's like we do have two radiators in this case. So one is this disk, and then there is a second radiator, which is the radiator of the spacecraft, for instance. So when the temperature of the hot plate increases, then the cylinder, which does have a higher thermal expansion coefficient, will increase more than the expansion of the central flexible rod. So as a result, connection will be made between the disk and the cylinder. So then conduction heat transfer will also occur, and then the disk, the disk here will reach a higher temperature, and then it will radiate a higher rate of radiation energy to the radiator of the spacecraft. So that's how this switch works based on differential thermal expansion concept. So the technology readiness level of these devices may be different. Some of them have been used and tested in different flights. For instance, the one in the previous slide, but some of them are like concepts or they have lower level of TRL. This is another type of heat switch that we are going to talk about here, and this is a gas gap heat switch for cryogenic applications. So for cryogenic applications, usually a like liquid nitrogen is used, so it's a precious liquid, so it has to be used only when it's needed. So the use of a switch is important. So how does it work? So let's look at the schematic. The switch has a hot block and it does have a cold block. And the cold block is attached to the cooling source, such as the liquid nitrogen, for instance. So we only want to cool the hot block when it's needed. So in general, there is a gap. There is a gap that you see here between the hot block and the cold block. And this gap is, for instance, can be filled by a gas. All right. So let's read through this. So heat flows from end to the end across the narrow conical gap. So when the gap is evacuated, so when there is no gas here, a small amount of heat is transferred across the gap just by radiation. So in this case, the switch is off. And let's say the liquid nitrogen will not be consumed. So when the gap is filled with, let's say, hydrogen, so when this gap is filled with hydrogen, heat transfer is enhanced, so the switch is on. Even though it's a gas in between, still there is some level of conduction in the gap, so there will be heat transfer between the hot block and the cold block. So to turn the switch on and off, the gas is either absorbed or released from a reservoir containing a material, for instance, zirconium nickel hydride, which is actually embedded in charcoal. So, and that's the source of, that's the reservoir that we talked about. So the hydrogen gas can be absorbed or released from this reservoir, which contains charcoal with zirconium nickel hydride. So this charcoal has the capability of releasing and absorbing hydrogen. So how to activate that, how to actually send a signal to activate this. So this is done by this process. So the materials absorb gases at low temperature and expel them at higher temperature. So therefore, if the reservoir here is at a higher temperature, it will expel gas, but if the temperature is low, it will absorb the gas back, and the hydrogen will be going back to this reservoir. So in order to make that happen, in order to control the temperature of the reservoir to release gas and absorb gas, this is done by heating. So when the sorbent bed is actively heated, so like for instance we connect the electricity, typically with an electrical resistance heater bonded to the outside shell of the sorbent bed, gas is released to pressurize the gap and turn the switch on. So the heater is turned on here, it releases hydrogen. And as we turn off the heater, it will absorb the hydrogen back, so the thermal switch will turn off. This has been also proposed in this paper that you see here. So this is like a concept. I'm not quite sure whether this has been used in a flight or not. All right, so now let's switch to phase change materials, and which is one important thermal solution, especially for instance during the re-entry of the spacecraft to the atmosphere. or it's used when we want to have an isothermal temperature. So therefore it's used for space suits where a uniform temperature is needed. And the reference for this part is mainly from the reference 1, the Spacecraft Thermal Control Handbook. The previous section came from various sources for the thermal switch, and this part mainly comes from the Spacecraft Thermal Control Handbook. All right, so let's see what is the definition of a phase change material. So a phase change material is a substance which releases and absorbs energy during the phase transition, like during a phase change from solid to liquid or liquid to gas. That's phase change. So during phase change, a lot of heat is transferred, heat of fusion or latent heat of fusion and latent heat of vaporization. So a lot of heat can be transferred during phase change, much higher than the heat that can be transferred during sensible heat transfer. So during phase change, the temperature of the material, like a water-ice mixture, the temperature doesn't change. It's an isothermal process, if you remember from thermodynamics. But a lot of heat can be transferred, HFG, the enthalpy of from the liquid to the gas, that's the latent heat of fusion. So that's the concept. So PCM thermal control for electronic components is used for short duty cycle components in launch or re-entry vehicles, short duty cycle components. Although such components are used only once, they generate large quantities of heat that must be removed. Like for instance, during re-entry of the vehicle, a lot of heat will be generated because of the friction between the surface of the spacecraft and the atmosphere. A lot of heat is generated. If this heat is not properly absorbed, then it may end up basically overheating the surface and burning and crashing the spacecraft. So this is just like a one-time process, re-entry, but it's a very important process. And phase change materials are usually used during this stage because phase change materials can absorb a lot of heat in a short amount of time because of the phase change property or the phase change process which is involved here. And the phase change materials, using phase change material is a passive thermal management system, so it is reliable because there is no moving part. So PCM thermal control is useful for electronic components that operate in on-off cycles. So they have multiple uses. So one was like in the re-entry of the vehicle, but there are multiple uses. So when the component, this is another use. So when the component is on and generates heat, the energy is stored, for instance, in the PCM. Let's say an electronic box is generating heat, so it gives the heat to the PCM. But when the component is off, then the heat of fusion energy is removed and it's given to the radiator to freeze the PCM back in preparation for the next on portion. So by doing this, we can reduce the size of the radiator. So instead of using a large radiator to continuously and in a steady process remove all of the heat from the electronic to the radiator, we may use an intermediate PCM which can absorb the heat and then gradually in a longer time duration give it away to a radiator which has a shorter or which has a smaller surface area. So one application was like in the re-entry vehicle, when just for one time the phase change material absorbs a lot of heat. This is a one-time process. And then in an on-off cycle, this is another process. So it absorbs the heat, it melts, and then when the electronic box is off, then it's the time to actually give away the heat from the PCM to the radiator and let it freeze again and become solid and ready for the next cycle. So the alternative melting and freezing of the PCM enables the component to operate very nearly isothermally at all times. So it can operate at isothermal temperatures because during phase change, PCM temperature does not change. And the use of PCM results in a radiator that can have a smaller size when PCM is used. Of course, there is like a question that is it economical, because PCM is not free and it does have its own mass. So some design considerations and trade studies aren't actually needed. Another application of PCM is heat sharing. So let's say we do have multiple electronic components. So here on the left, we have multiple electronic components, and then we do have a PCM like material, in a let's say in a box. So each of these electronics are connected to the PCM using heat pipes. And now let's assume that some or one of these electronics generates heat. So the heat will be transferred to the PCM. And then some other electronics actually do need heat. They need to be heated. So instead of using heaters, then the heat required by the other electronics can be provided by the heat which is available in the PCM. So that's heat sharing, similar to a mechanically pumped fluid loop, which does heat sharing function. A PCM can also do heat sharing. This is another application. So this is another application and a video here that you can go ahead and watch. So a satellite orbiting Earth encounters different thermal environment as it passes in and out of the Earth's shadow. So during the eclipse of the satellite. So during such a mission, a PCM package can store and release solar energy to damp the otherwise large temperature changes that the spacecraft would experience during the orbit cycle. So if, for instance, for a particular type of satellite, it is needed to keep a very close to uniform temperature, PCM can be used because when the satellite is exposed to the sun, it's exposed to a lot of heat. So the PCM can absorb the heat, and then as it goes to the shadow, it becomes very cold. Then that heat can be released. Instead of turning on heaters, the heat from PCM can actually release and be given to the component. So essentially it works like a battery, right? So battery actually stores electricity, charges. So during when the spacecraft is exposed to the sun, the solar panels generate electricity, and then some of that electricity is stored in the batteries, rechargeable batteries. And then when there is no sun, when there's no sunlight, the energy of the battery will be used to turn on multiple heaters in order to keep the temperature of the spacecraft, multiple components, in the allowable limit. So PCM is like a battery which does store directly heat, not electricity. Some other applications, PCM can enable a crew compartment or a space suit to remain nearly isothermal throughout the orbit. It would be enveloped by a layer of PCM, so like in an astronaut's spacesuit, which was the front cover of this presentation as well. That there was a astronaut with a spacesuit. So a layer of PCM that would absorb, release heat as needed in order to keep, for instance, the temperature at the right temperature. So PCM can be used in a spacecraft that lands on the surface of a planet, which undergoes days and nights as well. For instance, for the moon missions, 14 days, according to the Earth, 14 days on the surface of the moon will be the day of the moon, and 14 days will be the night of the moon. So if the mission is going to take, for instance, more than 14 days, then there will be like the spacecraft would experience day and night. So PCM can be used in such cases because there is a very huge temperature difference when the spacecraft is exposed to the day of a planet compared to the night of a planet. It's a huge like difference in the thermal load that will cause, that would essentially need a very complex thermal solution. So PCM materials probably can be used in this case as well. So storing energy during the day of the planet and then give it to the components during the night of the planet. So PCM packages can be integrated into experimental instruments to maintain thermal stability or ensure isothermal conditions during the experiment. That's another application. Let's say, on board International Space Station or for another in another mission, there is a need to create an isothermal environment for a particular experiment. For instance, a scientific experiment. PCM materials, because of the phase change process at constant temperature, have the capability of generating an isothermal condition and thermal stability. So they have been used, so this is not new, they have been used in the Apollo mission, Apollo 15 in 1971. So the rover used 3 PCM packages, which you can go ahead and read the details here. So it's not actually new. But since then, it has not been actually in many, because in satellites, usually like heat pipes are used and optical coatings and blankets. So they are used for, for missions which actually do need a complex thermal solution. Also for re-entry vehicles, space suits. So what kind of materials are used as PCM? So the phase change transformation can occur in the following processes: solid to liquid, which is the fusion, melting or freezing. So the heat is called the heat of fusion. This is the most common type. Fluid to liquid, solid to liquid, liquid to solid. It can be also done in the form of liquid to gas, a process, phase change process, which occurs also in heat pipes. So heat of vaporization is actually much higher than heat of fusion. However, there is a huge change in the volume of the fluid during this process. It can be done also during solid to gas sublimation and also during salt transformation. there is also some heat of some latent heat releases or absorbs during the salt transformation. Because some salts are like hydrous, anhydrous, whether they do have molecules of water or not. So that attachment and detachment of the molecules of water from and to the salt requires a lot of heat. So usually vaporization and sublimation of solids are used in open loops, one-time use. Let's say during a process, let's say enter it to the atmosphere, a lot of heat is released and then the vapor is vented. So this process basically absorbs, like ice to vapor process absorbs 3004 kilojoules per kilogram. This is about 10 times the heat of fusion of water to ice, ice to water. It's a lot of heat. So you can go ahead and watch this video about PCM used in re-entry vehicles. So some common solid liquid PCMs. So there are different materials, organic, inorganic, eutectics, natural, inorganic. So we are not going to go through the details. So a lot of chemistry involved. So in this you see water, as simple as water, which does have a large heat of fusion, which is the heat required to convert 1 kilogram of ice to water and vice versa. So these are materials that actually change phase around the room temperature, like 0 degrees C and negative 25 to like 37. So there are, if for emission for a particular process, the temperature, that the isothermal temperature which is needed is very different from these materials, then other materials are available as well. For instance, alcohols freeze at a much lower temperature. So if the isothermal or the phase change temperature needs to be much lower, for instance, alcohols can be used. Alright, so that was the end of the phase change materials. I'd like to talk about heat sinks as well. Now that we are talking about phase change materials, it's interesting to note that the heat sinks, which are used in laptops, in computers, in electronics, so these aluminum blocks, oftentimes with the fins, these are heat sinks, and they are usually made of aluminum. So why these are used? Because these are actually, they do a job very similar to phase change materials. Even though there is no phase change, aluminum always remains solid, but they do have the capacity of absorbing and then releasing heat. So PCMs store release heat based on their heat of fusion or latent heat phase change. Solid, liquid, liquid, solid. A solid heat sink can be also used to store heat without phase change, because they do have a heat capacity. So thus a heat sink stores sensible heat. Sensible heat means the heat transfer is because of a temperature difference, and as heat is added, the temperature will go up and go down when heat is removed. So a specific heat capacity, Cp, or simply C, for solids we have only C, Cp, Cv the same, equal. So a specific heat capacity of heat sink material should be high. That specific heat capacity is the amount of heat which can be absorbed or stored per unit mass per degree C. It appears that here I do have a wrong unit for Cp. The unit of Cp should be kilojoules per kilogram per degree C, or per Kelvin or Fahrenheit. So that's the definition of the specific heat. How much heat can be absorbed in 1 kilogram of aluminum when its temperature increases just 1 degree C. That's the specific heat. So base materials for heat sinks or aluminum are materials that have actually a high CP. So aluminum has a CP of 0.9 kilojoule per kilogram degree C, magnesium 1.02, beryllium 1.88. So you see beryllium has a CP double that of aluminum, which is good, but it's more expensive. So for a space application, it may worth to use beryllium because in some cases mass is an important factor. So, and also ceramics of the above mentioned metals do have a high specific heat capacity as well. If you remember, Q is equal to mCp delta T. So if a material has a high specific heat capacity, then it can store more heat. Okay, so when to use a PCM, so a phase change material. So PCMs are generally useful for providing stable temperatures, isothermal cases, or for allowing radiators to be sized for average rather than for peak or for the corner cases. So we can actually size the radiator for normal operation, not for the peak or corner cases, and then use PCM for the case that the heat load is higher than that it's higher than what the radiator can actually handle. So the question is that is the reduced mass of radiator is higher than the mass of the PCM? Because we reduce, let's say if you size the radiator shorter or smaller than what it should be for the corner cases, how much mass you can save? Is it less than the mass of the added mass of the PCM? How about the cost, the complexity, and so on? And in most spacecraft applications, multiple thermal solutions are evaluated, and one with lowest mass and power requirement, cost and development complexity, and high reliability is selected. Sometimes it's required by the customer that actually the technical team should perform a feasibility study and show that what is the benefit of using, for instance, one thermal solution versus the other, and then choose the best one. So the level of priority of each of these criteria, for instance, mass, cost, complexity from one another, can be the determining factor about which solution, for instance, to choose and to go with. And here is worth mentioning about the interface between the components and PCM. So always when we want to connect two solid surfaces, because of the roughness between the surfaces, there are many gaps, micro and nano-sized gaps between the surfaces, and these gaps actually hinder the heat transfer rate. So here, if you look at here, the two surfaces are quite smooth, so there's not much gap, but sometimes the surfaces are wavy. So of course, first we need to make sure that the surfaces are very smooth. And beside that, filler materials can be inserted between the components and between the two components. In this case, one component is, for instance, the electronic box and the PCM material, which is stored in another box. So filler materials can be used to decrease the thermal contact resistance. Some filler materials are like carbon fibers. Carbon materials are highly conductive. They are very small. They have small sizes, so they can fill the gaps. Copper foam. So copper is very conductive as well. It's ductile. Copper is ductile, so when it's put between the gaps and compressed and pressed, it will fill the gaps. Also different materials, aluminum foams, and so on. So when these fillers are inserted between the two different materials, they will go ahead and fill the gaps. So the thermal contact resistance can be reduced, therefore heat transfer rate will increase. Without these fillers, and if the thermal contact resistance is high, the heat transfer rate will substantially drop and the thermal solution may not work. So the last slide of this lecture, the choice of the PCM. So the PCM that we want to choose, it must have multiple characteristics. For instance, of course, it should have, right, we mentioned that it should have like high heat of fusion. So this is like it should have high heat of fusion. It should have high thermal conductivity because heat is going to pass through the material. Specific heat CP has to be high in order to be able to store a lot of heat. Density should be high, and volume change during melting. So the volume change during melting should be low because you don't want your phase change material to undergo a very large volume change. And some other factors, availability, cost, for instance, low cost, compatible with other materials and fillers, no chemical reaction, no toxicity, obviously. So these are some of the properties of the phase change materials. And one of the main phase change materials which is used are like different kind of waxes, paraffin wax, which is currently used as phase change materials. Okay, so this brings us to the end of this lecture, phase change materials and heat switches. So heat switches was taught next to phase change materials. The reason is that they have a very similar functionality, and some of the heat switches actually use the paraffin wax for the actuation. So in some ways they are similar, but they are two different things, but they were combined and taught in one lecture. Thank you very much for your attention and hope you enjoyed this lecture. Feel free to send questions via email or course forum or write comments under the video. Thank you. Bye now and see you next time.